Good morning, guys. Happy Friday. I have another collision problem here, and I think some of you may be happy that it's not inelastic this time. I know we covered a bunch of those, so it's time to move on to elastic collisions now. Similar concept, but with some noticeable differences. For this problem, all we're doing is taking a tiny ball, which I'll refer to as A, and we're throwing it horizontally at a more massive ball, which will be referred to as B. A will move in and collide with B elastically and then bounce off in the opposite direction at some other speed. Notice that B will have some non-zero speed as well. We need to figure out those speeds and then use them to get the tension in the wire. Let's start with momentum. The initial momentum comes entirely from A, and the final will be the sum of the momenta from A and B. Here's where we run into a problem, though. There's one equation here and two unknowns. We don't know what the final speed of A is, which should be negative in this coordinate system, and we're clueless about the final speed of B as well. And all of these velocities in this expression have different values. So, what is it that we're supposed to do here? Remember I said that elastic collisions are different. It's because they conserve both momentum and energy. We're going to take advantage of that to dig ourselves out of this hole. Let's grab this momentum equation in front of us and then also get the conservation of energy equation as well. The plan is to combine these. The first thing we need to do is to put the quantities in both equations that contain the massive A over on the left. We can factor out the mass of A in the momentum equation, and then we'll get rid of the 1/2 in the energy equation in order to apply the same idea and factor out A as well. Notice that we have a difference of squares inside the parentheses of this energy equation. I'm going to rewrite that using the following identity. For reference, let's call the top expression equation 1 and then the bottom one equation 2. Our next step is to divide equation 2 by equation 1, like this. And when we do so, a bunch of things are going to be eliminated. The masses of A will cancel each other out. The parentheses containing the difference of the two velocities will cancel each other out. The masses of B will cancel each other out. And then finally, one factor of B's velocity in the numerator will cancel out the single one in the denominator. And so after all that stuff is removed, we get the following. Let's call this equation number 3. We're going to take equation number 3 and plug this back into equation number 1 on the right-hand side. Let's go ahead and distribute the masses into the parentheses on both sides. And then we want to collect everything with an initial velocity on the left and a final velocity on the right. We'll factor the initial and final velocity out on both sides, and that allows us to divide both sides by the sum of masses on the right, which gives us an expression for the final velocity of A. So that's cool. Let's call this equation number 4. There's one last step, since we need the final velocity of B as well. Let's go ahead and take equation number 4 and plug that back into equation number 3, like this. We need a common denominator on the left, which means the first term needs to be multiplied by the following factor of 1. With the same denominator on both terms, they can now be combined, like this. And the initial velocity of A exists in both terms in the numerator. So we can just factor that out. Notice that we're adding the same factor of B's mass that we're subtracting inside these parentheses. So let's go ahead and remove those. With those gone, here's what's left. And this expression can be further simplified to this. And we'll call that equation number 5. So we've gone through all of this work. We picked up 5 different equations along the way. And now we have an expression for the final velocity of B. Let's see what the value of that is. If I plug in the numbers, here's what we get. 2 meters per second in the positive direction immediately after the collision. That velocity is what we'll use to get the tension. To do that, we're going to need to draw a free body diagram. Following the collision, there's the weight of B pointing downward and the tension from the wire pointing in the opposite direction. These two forces on their own are not enough, though. We also need to consider that after these two balls collide, B is going to swing to the right along the path of a circle, as we've seen from multiple problems in this chapter so far. And that implies that a centripetal acceleration vector is necessary in this diagram. With that said, let's move on to a sum of forces in the y direction next. I'm going to plug in the definitions for the weight and the centripetal acceleration of B, and then we can move the weight term over to the right in order to isolate the tension. The mass of B is attached to both terms here, so let's go ahead and factor that out, and now we're free to start plugging in some numbers. Enter this into a calculator and truncate to 3 significant figures, and you should get the same answer that I did. 102 newtons. That's all there is to it. Thanks for watching, everyone. Have a great weekend.